Okay, so we're going to continue the TASI tradition of always starting on time. It's nice to see everybody here bright and early. That's probably because it's the first week, right? So on my wiki, the Twiki, I posted a talk by Azatov, who's a young postdoc at CERN, and this talk has Higgs physics in effective field theory, showing how you might analyze Higgs production in an effective theory and how this analysis extends when you're looking for two Higgs production. So if you're interested in the effective theories and Higgs production, this talk is a very nice general overview. I hope to get to some of that today, but I have a bad feeling I might not get to it. Okay, so in Chabas' talks yesterday, you heard about all the reasons why you might go beyond the Higgs mechanism. In particular, I think what you should take home from Chabas' talk is that if I calculate the renormalization of the Higgs mass, it's quadratically sensitive to new physics. So if there's some new physics up there, you're going to see it in the Higgs sector. So that's very nice. Okay, so today I'm going to finish my test case of glue goes to Higgs. And let me top Higgs. I calculated this in exquisite detail last time, and somebody said, well, what about the cross diagram? And of course, it's there. This guy is equal to this guy, and the relative factor of 2 is in my final results. So I didn't forget about it. I actually triple-checked that my 2's are right. So they're identical, and they're, of course, both there. Okay, and what we derived last time was that the Lagrangian is equal to alpha s over 12 pi v h g mu nu. A is a color index, of course, g mu nu a, in the large MT limit. Now, it's possible to derive this result without actually calculating any diagrams, and like I said, the Russians did this years ago. So let me just remind you how the Russians derived this way back when. So suppose you're calculating something or other. I don't care what. This is some process X. This is a top quark here, and here's a Higgs. So I've got some loop diagram that results from the Higgs coupling to the top quark. And I'm going to call this internal loop momentum K, and this guy will be K minus pH. So if I calculate this amplitude, it's something or other from all this stuff that I don't know what it is. There's a propagator from this first top quark, K slash minus M, minus I M over V. So this is the top Higgs coupling. I over K slash minus pH minus M, which goes to the same dot, 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 I over M V, did I have the V there? Yeah. 1 over K slash minus M squared, which you can all tell is the same stuff, I M over V d by dm of 1 over K slash minus M. What's that? As pH goes to 0. Yes, as pH goes to 0. Thank you. So taking pH goes to 0 is the same as taking MT goes to infinity. It's the ratio that counts. So this is the famous low energy theorem, which says that the amplitude for making anything plus a Higgs is equal to M over V d by dm times the amplitude for making X. In the limit, pH goes to 0. Okay? So this is kind of nice. So it's just the derivative of the amplitude. These guys are unrenormalized. unrenormalized quantities, so when you use this to calculate higher orders, you got to worry about getting the renormalization right. Okay, so this low energy theorem is extremely useful. So let me show. Yes?
So when you set pH 10 to 0, you're comparing it to another.
Yes.
What
So,
is that?
well, in this case, it's always going to be MH over MT. This just formally says pH goes to 0. Yeah. Anything. This is any final state. Yeah, so this is, that's why it's complicated when the Russians did this. It's got lots of formalism and stuff. So, got any final state, but as long as there's a top quark coupling to the Higgs, this is true. And in fact, you can drive this by making pictures where Higgses are stuck in various ways in diagrams, and it gets all the combinatorics right. Top mass. Let me put some mass in the loop. Yeah, it's a top mass here. It's any heavy mass, okay? So it's extremely useful if, for example, you have a model with lots of heavy stuff. Okay, so let's just take this one step further. Okay, so my QCD Lagrangian is equal to minus a quarter G mu nu, G mu nu. And let me get my minus signs right here. So can you see it when I do it like this? Part way up? Okay. So G mu nu, D mu G nu A minus D nu G mu A plus G FABC G mu A G mu B. Okay, so that's the gluon field strength. And what you can do to pull this G out is if I define G prime mu equal to 1 over G mu, okay? So I'll just define with the G pulled out. The lattice guys like to do this. But what happens then is very useful for this analysis. So L is equal to minus a quarter G squared, G prime mu nu, G prime mu nu. Okay? So all the G's are just pulled out front. So now I can use my low energy theorem to get the coupling of the Higgs to the gluons here just from this. So L effective is going to be equal to M over V d by dm. What shall I call this? L naught of L naught. Okay. Almost done here. Okay, so if I'm taking d by dm of L naught, I essentially get d by dm of G squared. Anybody know what that is? You guys remember what the derivative? Well, when I write it down, you'll remember. All right. The beta function is mu dg d mu. Okay? So you can see what's going to happen is I'm going to get the coupling to the Higgs in terms of the beta function. Okay, d by dm of L naught is d by dm of 1 over G squared. Since dg d mu is m here, the mass scale, it's the beta function. So the effective Lagrangian for a Higgs coupling to heavy fermions is equal to minus 1 over 4G squared, 1 minus 2 beta over V, H times the Higgs, times G mu nu prime G mu nu prime, where this beta only has the top quarks, because that's the only thing that comes in, so I'll call it beta F. So beta F over G beta over G H over V, is alpha S over 6 pi, which is indeed the result we derived by exquisite calculation. But this is actually very useful for Higgs physics because, for example, I can use the beta function for heavy colored scalars, and I actually get the right high energy limit. I got some weirdo model with lots of heavy vector fermions. I can use this result. So I can get the heavy mass limit of the Higgs coupling from this. So this is called the low energy theorem, and it's extremely useful. Heavy fermions, yeah. In this case, yeah. Anything. Anything other than, no, it can be anything. It can be anything. Works for anything. Well, so what is the assumption when you do this? The assumption is that the mass of the fermions that are contributing to this coupling are much, much heavier than the mass of the Higgs. That's the only assumption that goes in here. Okay, so this theorem that we have up there, you can apply it again to get the coupling to 2 Higgs, 3 Higgs, 4 Higgses, and whatever, just by keep going, taking derivatives. And you get the right coefficients, combinatorics. And what happens is you build up a logarithm. So you build up a log m for the h over v, g mu nu squared, g mu nu. Okay? So what happens is rhythmic dependence when you keep applying that. And I'm not going to derive that right now. Okay, so that's finishing up on the low energy theorem. All right. So I talked a lot about glue glue goes to H. Let me just remind you that it's exactly the same if I want to have H to gamma gamma, which was one of the discovery modes of the Higgs, right? So I have H. I've got this top quark loop, gamma gamma. This is exactly the same calculation we did yesterday, of course, except they're electromagnetic couplings here instead of the gluon couplings. And then I've got W, W, H goes to gamma, 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 and I've got H. Okay, gamma, gamma, W, W. So it's a straightforward calculation. You get the branching ratio. H goes to gamma, gamma. It's about 10 to the minus 3. But it's a little bit different from glue glue goes to Higgs in the sense that when you have the photons, these guys dominate. So there's actually a minus sign between the contributions of these guys when you work out the numbers. So they tend to cancel, and these guys are much, much bigger. Yes? Yeah, yeah. Depends on your gauge, right? But yes? Oh, yeah, I do know, but well, you do have those things, and you have to calculate them, and they're gauge dependent, right? So you have the Goldstone bosons, for example, which is what you're referring to. So they're the Goldstone boson components of the W's. So you want to well, me being lazy, I would calculate in Feynman gauge where you don't have those things. So it's a gauge dependent choice. So if you pick your gauge carefully, you can have more or less work. Yeah. So, okay. All right. So H to gamma gamma, it was a discovery mode. And how did that work? Okay. At the LHC, this was a discovery mode, but we start by saying there's lots of QQ bars goes to gamma gammas that have nothing whatsoever to do with the Higgs. They're just gammas from stuff like this. Q, Q, gamma, gamma, right? Nothing to do with the Higgs. So here's d sigma dm gamma gamma, and here's m gamma gamma. And it falls kind of like this. And this scale here is a logarithmic scale, so it goes over many orders of magnitude. And then what we do to get out from the interesting stuff is we put in the contribution. Glue, glue goes to H, goes to gamma, gamma. And it's a little bitty pimple here. So what the experiments do is they fit to this steeply falling background away from the Higgs signal, and then they subtract. So if you fit to that, you're going to have a flat line, and here's the Higgs bump, right, by subtracting the fit, which you call fitting to the sideband. So you fit up here, and you fit down here, some polynomial function. Then you subtract it, and you get your bump. Okay, so people who are thinking about resonances would say, aha, that's a resonance. I can measure the width of a resonance. The problem with this is that if I add up all the decay channels of the Higgs, let's see here. I think I'll move over here. If I add up all the decay channels of the Higgs, gamma H, let's call it theory, is on the order of 4 MeV. Okay? The detector resolution over here is a few GeV. So you can't measure the Higgs width just by classical techniques of looking at a resonance because it's too narrow. Okay. So let's contrast this with an E plus E minus collider. Okay? If I had an E plus E minus collider, so E plus E minus goes to a virtual Z, which then goes to a Z and a Higgs. And this Z is going to go to two lepton pairs. I don't know, L1 and L2. Okay. So in this kind of process, I would know the energy of the electrons because it's not like a hadron collider where the energy of the partons is smeared by PDFs. I would know this guy. So this would be P1, say, and this would be P2. And these leptons, let's call them, I don't know, K1 and K2. Okay? So then if I construct an object which is P1 plus P2 minus K1 minus K2, call this guy K3, by conservation of momentum, this guy squared is equal to K3 squared, right? So I can measure this thing, right? I measure the momentum of the leptons. I know the incoming momentum. So I know K3 squared. Okay. So this guy, this quantity, which is called the recoil mass, is going to have a bump at the Higgs mass. So in an E plus E minus collider, I can pick out Higgs production without saying anything about the Higgs decay. Okay? So people love this, right? I don't have to make assumptions and look for various Higgs decays. I can just pick it out that way. So I can measure sigma ZH. Okay? Oops. But now I can say, aha, I know it's a Higgs production. So now I'm going to look for the decay for H goes to leptons. Okay? So I can measure the decay H goes to leptons. So I know everything about this. Okay. So sigma ZH and then H goes to L plus L minus is equal to sigma ZH times the branching ratio of H goes to L plus L minus. Okay? And I can measure both of those guys, right? So then this guy is gamma H goes to L plus L minus over gamma H total. Okay? So then, by putting together this stuff, I can get a measurement of the Higgs width without making assumptions. And that's what people really like about the E plus E minus machines, is that you could, by measuring ZH and then the decays to leptons, I can get the total width. I just measure it. Unfortunately, we can't do that at the LHC. So we have to be cleverer at the LHC. Yeah?
So do you assume that leptons are better measured than what?
Well, the rate to gamma gamma is 10 to the minus 3. But I can measure the leptons very, very well. Yeah. Yeah.
So you're saying that hadron collider there's too much
Nope, I'm saying in a hadron collider. In a hadron collider, I don't know the initial state of these quarks, right? Because the quarks are smeared over PDFs. So I don't have this information. Whereas in an E plus E minus collider, I know the incoming energy. So I have an extra variable. So I can pick out Higgs decays without saying anything about the Higgs, or Higgs production without saying anything about the Higgs decays. Just count. Oh, because I know I have a Higgs production because I'm making a cut right here, right? Oh, you just count, right? You just count. Any final state will do. But you see, I can measure two things. I can measure this guy, right? And I can measure this guy. So I have two pieces of information. That's okay. I put them together. Yeah, we can do it in the break. You have two pieces of information is my point, right? What's that? Oh, you can make cuts, though. That's the whole point here, is I know I can pick out this by measuring the recoil mass. Okay? So the whole point about an E plus E minus machine is I can recognize a Higgs production by measuring the recoil mass without saying anything about how it decays. Yes, absolutely. It's a bright Wigner, for example. Yep. Okay. So since we don't expect to have an E plus E minus machine in the next umpteen decades, we got to be smarter. Okay? We got to see if we can do this at the LHC.
So I missed the era of E plus E minus machine.
What's that?
So I don't know like how precise is P1 and P2.
Oh, in an E plus E minus machine, they claim they're going to get all this stuff to a few percent.
Oh.
Yeah. Depends on the Snowmass 2013 study, which was studying the future of physics, was highly amusing because people who were promoting different machines wanted to prove that their machine was the best, right? Everybody wants to prove that their machine is the best. So everybody said, well, I can measure the Higgs decay width to 5%. Well, I can measure it to 2%. Well, I can measure it to 1%. So when we were done, the ILC, which is the E plus E minus proposal in Japan, had measurements to 1%. But how did they do that? They ran it for 18 years. So their 1% measurement, I mean, the longer you run, the better you get, right? The precision essentially goes with the square root of the luminosity. So you gain with essentially the square root of the time. So you run for 18 years, you do okay. But, okay. And that's essentially the LHC plan, too, by the way. To get Higgs couplings to 5%, they're going to run till, I believe it's 2037. Okay. So when I make the joke that it's my nursing home plan, nobody ever laughs. But it's a long time from now, guys. Should you laugh? I don't care. I don't care if you laugh. It's not that funny. It's your nursing home project, too, maybe. I don't know. It's 20 years from now, at least. Right? So it's not a good bet for a young guy. Okay, so we want to do better. We want to actually measure the Higgs decay width in an indirect way at the LHC. Okay, so first of all, how are we going to parameterize how the Higgs scales with new physics? Well, what we're going to do is have these fudge factors, which people call Kappa factors. Right? I've introduced these before, explained that it's not the greatest way to do things, but it's the way we're going to do them for now. So here we have, say, glue goes to Higgs, goes to some, actually I don't even need to make it glue. Let's just make it anything. Let's make it I. So if initial state, final state. So how am I going to parameterize this? I'm going to parameterize it. It's typically something that's called mu. It's going to be the cross section for II goes to H goes to JJ over the same thing. II goes to H goes to JJ standard model. Okay? So the denominator, let me put a shout out for the people who do higher order corrections. These things are calculated, exquisitely precisely. Okay, so this thing is going to be sigma II goes to H over sigma II goes to H standard model times the branching ratio. H goes to what I call JJ over the branching ratio. H goes to JJ standard model. Okay, because we're always going to assume the Bright-Wigner approach works. And since we actually think that the Higgs width is 4 MeV, we suspect it's pretty good approximation. Okay, so this thing is going to be, at this vertex, I'm going to have, say, a kappa I, which is going to be the ratio of the coupling to the standard model coupling. So this is going to be, say, GI over GI standard model. So this is how I allow my Higgs couplings to vary by kappa I. So this vertex will give me a kappa I, and this vertex is going to give me, again, a kappa J. So this thing is going to be kappa I squared, because it's cross-section, it's squared, kappa J squared over kappa H squared, where kappa H is going to be gamma in my model over gamma total over gamma H standard model. So I'm going to allow for a rescaling of the total width too. Okay? So these scaling factors are just kappas, and I'm going to try to measure this. Of course, you notice instantly that there's a blind direction here, right? Okay? If I take kappa I goes to, I don't know, chi kappa I, and kappa H goes to chi squared kappa H, it's blind. I would be not able to measure that. Okay, so all right. So very fine. So we're going to try to use a new idea to measure the Higgs width from glue goes to ZZ. Glue goes to ZZ. This is an idea that Kirill Melnikov and Keola Fabrizi, that's his name, who was a postdoc at Hopkins at the time, they had this really clever idea that had people like me saying, "Bill, why didn't I think of that? It was so obvious. We should all thought of it 20 years ago." But okay, so this is a really cute idea. So let me just remind you, okay, you've got diagrams. Glue goes to H, goes to ZZ. These are the guys that I'm super interested in. But of course, there's also lots of other stuff. Glue goes to Z, GG. Ooch. And in this case, since this isn't a Higgs, since this is a Z, these guys are mostly the light fermions that run around this loop. So this guy is mostly the top quark, just to be pedantic. So I'm mostly going to talk about this piece. But when the experiments actually do this analysis, let me assure you that they put the whole thing in. Okay, so an aside for how the kinematics goes, because we haven't done kinematics, and I don't think Matt did this one either. So let me just remind you that as in the E plus E minus case, you knew the initial state energy. In a hadron collider, of course, you don't know the initial state energy of the partons. So what I have is sigma pp goes to, say, ZZ. So this is the hadronic interaction. It's equal to the integral dx1 dx2 sigma hat of S g of x1 g of x2, where these guys are the gluon PDFs. Okay, and sigma hat is the partonic cross-section. So this is the cross-section for these partonic processes with the partonic energy of S. So then we're weighting by the gluon PDFs. Okay, usually what we do is we change variables to a more convenient set, okay, where the hadronic energy, so this guy is, say, 13 TeV squared, that's the S, is equal to little s, the partonic energy, over a variable tau, at x1 equals square root of tau e to the y, x2 equals square root of tau e to the minus y. You'll see why I'm doing this in a few minutes. So this cross section here, sigma pp goes to zz, is equal to the integral d tau dy sigma hat of s g square root of tau e to the y g square root of tau e to the minus y. Okay, this thing has better convergence properties than integrating over x1, x2, and in fact it tends to be flat in y. But the point for what I'm going to say in a minute is that this integral over d tau is actually 1 over s hadronic times an integral over ds times the rest of the stuff. So when I'm calculating the partonic cross-section, I'm actually integrating over the partonic center of mass energy. So not only is it not fixed, but I'm integrating over it weighted by the PDFs. Okay? And we'll need that. Okay. Let's see. All right. Okay. Okay, so how does this argument go?
Sorry,
Yes?
With this common prediction, can you capture all the possible?
Sure, it's just a Jacobian. I just made a change of variables and put in the Jacobian. Yeah. It's just a Jacobian. And let me just belabor the point, is that actually when I do this, it tends to this tends to be very large as x1 and x2 go to 0, whereas this is flat in y, so the convergence is better. But it's just a trivial Jacobian change. Yeah. This is the way people usually do it, because then with this you can calculate, I don't know, d sigma dy, for example. Yeah? S is the partonic center of mass energy. And we don't know what it is. We're integrating over it. Yeah. Oh, there's the rest of it here. That I just didn't want to write out dy sigma hat g. I'm just lazy. Okay. Sigma hat of s. Okay? It's all there. I just made a change of variables. And the reason I did them is because what I'm going to say in a minute is easily understood if you realize you're integrating over their partonic center of mass energy. And again, let me say that the people who do this did it right. I'm just going to emphasize to you how it works, why it's so cool. Okay. Yeah? Oh, that's there too. Yeah. That's, yes. QQ, there's, of course, lots of other stuff. I mean, if I'm making ZZ, there's, of course, Q bar goes to Z. That's, of course, all there, too. Absolutely. Right? Different initial partonic states don't interfere with each other. Okay? So I can calculate this separately from this. But, yes, it's absolutely there, and it's big. Oh, this is bigger, right? Because this stuff occurs at a loop. I mean, this stuff is not as small as you would think because they're more gluons. So you sort of play off the gluon factor with the loop factor. Yeah.
So from this process, what do we want to learn?
I haven't gotten there yet. This was an aside on kinematics, since nobody's given you the kinematics. I haven't gotten to what you're going to learn. Now I'm going to tell you what you're going to learn. Yeah. What do you mean? S hadronic is 13 TeV squared. I mean, that's fixed. I'm doing an experiment. I know what that guy is. Yep. ATD, whatever. Yes, we know it. But we don't know the partonic center of energy. So we don't know the energy of those two gluons. We have to weight them with the gluon PDFs. Okay, very good. So here's glue, goes to H, goes to Z, Z. So this is the process we're really interested in, okay? So this guy is going to go like some kappa G, some coupling, and this guy is going to go like some kappa Z, okay? So the cross-section for this guy, wiggle sign, because there are, of course, interferences and all the other diagrams. This guy is going to go like kappa G squared. There's an integral over the partonic center of mass energies. That's his ds over there. S minus mh squared plus gamma h m h, I want to get this right here, squared, kappa z squared, epsilon z mu, epsilon z nu. Okay. So cross-section generically looks like this. We'll forget about integrating over the gluon PDFs and so forth for now. And we'll make a simple observation. Let's go above the resonance. Okay? So let's go to S much, much greater than mz squared. Okay? So then I've got sigma. It's going to go like kappa G squared. 1 over S. What's that? Yeah. No, yes, mh squared. You get the same answer with mz, but I do mean mh, yes. So kappa G squared, 1 over S, kappa Z squared, epsilon Z nu, epsilon Z nu. Okay. Let's see. Can you see if I write down here? Okay. So I'm used to thinking of a resonance, say the Z resonance at LEP. So LEP E plus E minus goes to Z.
Sorry, can I ask one question?
You can ask anything, sure.
Is this really sigma? How do I get the polar vector like that?
The total cross-section. So the total cross-section, I take the amplitude squared.
Yeah. But then
Yeah.
how do you see
I'm going to have to sum over the sigmas when I'm done. Oh, yeah. Right? So to do the total cross-section, I would take the amplitude squared, right? And I would have epsilon mu, epsilon nu, right?
But then it doesn't make epsilon anymore.
Well,
Right.
you'll see in a sec. I'm just being sloppy here. Yeah, I just want to show you a point. I don't want to do the whole thing, right? Because you can do the whole thing, and I actually don't want to do that. Yes, you should do that. But the point here is that I could do it, but then we'd be here too long. Okay, so let me be sloppy here, guys, and you're going to see the physics point, and then we can do it right if you want later. Okay, the Z at LEP is a bump, like that, right? It goes up at the resonance. Here's mz. And then it goes down. Okay, if I look at E plus E minus goes to Z, goes to, I don't know, mu plus mu minus, say. Okay? However, with the Higgs couplings to Z's, there's something different. And the something different is that these epsilon mu's go like p mu over mz for the longitudinal guys. This is where I'm getting at, right? Is that there's a longitudinal polarization here that you don't have at LEP. So when you're all done contracting the epsilons here, what you get is instead of 1 over S, okay, instead of 1 over S here, this thing is going to go to kappa G squared, kappa Z squared, over mz squared. Okay. So the 1 over s that's here, the epsilon polarizations are going to turn into p's, which are going to cancel the s, and you're going to get a constant piece above the resonance. So what's going to happen from the Higgs is that it won't look like this, but if as you go, so let's be GG goes to H goes to ZZ, is that it's going to get a tail out here, where this tail is from the longitudinal Z's. Cool, huh? You have to. You don't know if it's actually going to work numerically when you do it right, but the physics is really, yeah, you can't see. Let me. Actually, it does. In fact, when you look at the plots when they do it right, it kind of goes way out to constant. Yeah, it's cute. It really does.
If the Higgs mass goes to infinity, then that doesn't change. So
well, the Higgs mass doesn't go to infinity. So we're going.
You send it to. I guess.
We're going to very high energy. We want to say way above the resonance. It doesn't look like LEP, which is, oops. So now this is H, right? So you think resonances have this nice peak, but because of the longitudinal polarization of the Z, you kill this off. You get the longitudinal polarization is p mu over mz, so you kill off the 1 over s, and it just goes like the kappas over mz squared. So it goes to sort of a constant. And believe me, it really does when Keith Ellis calculates this to higher order. Believe me, it does. No, it works out this way, actually, when you do it this way. Yeah, really, yeah. Yep. And the reason is, let me give you a better answer, is because you're calculating all the amplitudes and squaring them together. So it's not really just this guy. I'm really calculating all the amplitudes and squaring them. So I'm picking out a piece here. Okay, I'm picking out the piece in the tail. Yeah, I should have brought a slide and put it up here so you guys could see the contributions. Yeah. Okay, but yes. Yeah, except for ZZ, you can reconstruct everything. So you can reconstruct the Z's go to leptons. For the physics is the same, right? The physics is the same. And in fact, John Campbell and the MCFM people have looked at that. But you can't actually do this thing for W's because this relies on the fact that the Z's are going to decay to leptons, right? Which you're then going to reconstruct. Okay, so. Well, I'm actually integrating, just showing you generically here. Yeah, I don't care, right? D sigma ds, because this thing is 1 over m squared. Yep. Yeah, d sigma ds. Yeah. All I care about is the fact that you're killing off a power of s from the longitudinal polarizations. Sure. This, like I said, I'm just trying to justify why when I actually calculate the full thing, it comes out to be different than this. And it's because of this longitudinal polarization giving you 1 over mz squared.
Normally, isn't there cancellation of leading propagation of vector growth? Just like you have. No.
Just by Higgs itself.
Oh, you don't. I'm just justifying it. Then I'm going to show you what the plot looks like when they the calculation that is done, which I will sketch you a plot of, is that diagram plus all the cross diagrams. So everything, all the polarizations, everything. But what I'm telling you is that you can generically understand that as you go to MZZ above the peak, you're picking out this longitudinal polarization where it goes flat.
Oh, really?
Oh, you add everything. You can't do it otherwise.
Then there must be cancellation.
Yeah, absolutely. I mean, I'm going to show you what it is. But the physics here, guys, is it doesn't look like a resonance like GG goes to Z, that it gets this tail at high MZZ, and the tail is exactly because of those polarization vectors. Yes?
Just roughly. Sorry.
Yeah.
Wouldn't it go to 1 over mc to the 4th? Go on.
I don't care.
Okay.
The fact is that there's no dependence on S. It goes to a constant at high energy. I'm being extremely sloppy about factors like that. Okay, why don't I finish this and then you guys ask, okay? Because I'm telling you, the final answer is just done calculating GG goes to ZZ with all the pieces and squaring it, okay? But, okay. Okay, there's no swindle in the final answer. It's a straightforward calculation. Okay, so now if I'm near the resonance here, did I erase it? Okay, I'm near the resonance up there. I've got kappa g squared. I'm integrating over the energy, 1 over s minus mh squared there, and I'm near the resonance. Okay, so Matt showed you the Breit-Wigner narrow width approximation, right? I equals integral over ds. Okay, s minus mh squared plus gamma h m sub h quantity squared. So near the resonance, I've got something like this. And the way you do this, how many people have derived the narrow width approximation? Anybody? Oh, okay. Small numbers. Okay, so you guys can snooze. I'll derive it right now. You can make a change of variables. Tan theta equal s minus mh squared over gamma h mh. So this is just a change of variables. So this thing then goes to the integral d theta over gamma h mh, where this is 0 to minus pi. Okay? Just by making a change of variables. So this thing, near the resonance, goes to delta s minus mh squared pi over gamma h mh. Okay, that's the narrow width approximation. So if I'm going up to my naive cross-section up there and looking at what I'm going to get near the resonance, I'm going to get sigma near the resonance is going to go like kappa g squared, kappa z squared over gamma h. Okay? So I'm on a resonance. I get 1 over gamma h downstairs. This is well known. Above the resonance, I don't have any dependence on gamma h, and it just depends on the kappa g squareds. So, big assumption here. Okay? If you assume that these kappas are the same above the resonance and on the resonance, you can see that something very interesting is going to happen. Oh, probably. Yeah, that's what the wiggle is, right? The wiggle says that the rest of this stuff is boring. Yeah. Yes, the wiggle says that I could do it and get all of my factors of 17 and 12 pi squareds right if you wanted me to lecture for 10 hours. So there's there's probably 1 over mz squared. Yeah. Some number, doesn't matter. Some number that doesn't depend on kappas or gammas. So what I'm claiming is that these two scalings get the factors of kappas and the factors of gammas right. So the bright idea, the light bulb idea, was that if you could measure the cross-section sigma above the resonance versus sigma on the resonance, it would be proportional to gamma h. So this ratio would give you a measure of gamma h. Okay.
If it includes the GG box as well, why would it just be proportional to kappa g squared, which is just the Higgs?
This is just being stupid. This is arguing for why this might work. Okay. So just look for glue goes to H goes to ZZ. Okay? You're just looking for Higgs to ZZ. And then you're saying that, if I just calculate glue goes to ZZ, I should have done it in gory detail. I could have spent the whole week doing it. Right? If I just look at that guy, and then I calculate d sigma dm 4 leptons. Okay, so let's let both of the z's go to 4 leptons versus m4 lepton. So I'm going to calculate now pp goes to zz, or Keith Ellis and John Campbell are going to calculate this, and I'm going to include everything. Okay? All these kinds of diagrams, all these kinds of diagrams. QQ bar goes to ZZ. I'm going to include everything. So I'm going to do it right. Okay? But now from this argument here, you think that it's not going to look like a resonance. I'm still going to see those longitudinal polarizations. And what happens is you have like this. So here's the Higgs mass. Okay? And if I were just like at left with a resonance, it would just come down. But what happens is it kind of goes like that. The various pieces interfere and stuff. But it goes out here, and there's a sort of flat part out here. Okay? So this is the full calculation with everything. And it shows these features. Okay? It shows this flat part out here, which is coming from those longitudinal z's. So this part you would not get from these guys and these guys. This part out here, 100%, I mean, it comes from the fact that the z's have longitudinal polarizations because of electroweak symmetry breaking. Okay. And it's actually kind of cool. About, 15% of the cross section is above M4L. Let's see, 140 GeV. Okay. So this is kind of cute. So what the experiments do is they measure this physical thing. They measure it above whatever. So if they put some cut here, 140, wherever. And then they measure on the resonance. So they put another cut here. And then they use some program, say MCFM, which includes the width here, to extract a width from this, because these arguments show that it's sensitive to the width. Okay? So you can't do this naive scaling that I was showing you, but it is sensitive to the width because of that. And what they actually get is that gamma H is less than on the order 4 to 5 times gamma H standard model. Okay. So now I'll stop and ask for questions. Okay. I wanted to get through this. Now, okay.
So in this analysis, are the three parameters just in addition to gamma H?
Oh, in this one, I think they just adjust gamma H. Yes, and that is exactly a problem with this analysis, right? And I'm going to continue in a minute and show you what happens. Yes, this analysis assumes that the couplings on the peak are the same as the couplings above the peak. Okay, so that is a big assumption, because you can see here the scaling comes from the couplings here on the peak to the couplings above the peak. So if they're not the same, and it's easy to construct a model, and you probably have, and I'll talk about it in a sec, that doesn't do that. So let me write assumes couplings same let's say everywhere. Yep. And that assumption is the number one criticism of this. Okay. Other questions? Yes.
Isn't it always why it's a bump? Like, why the second bump?
Oh, that's no, that's not it. It's the effective interference. Because you actually, if I had more time, I would talk about if you go up to those two diagrams on the top of the board there, they're top court, you have tops in both of them, so you see a unitarity cancellation between the two of them, so, which is actually very interesting.
But there's no bump at 2mz?
This bump isn't at 2mz, it's just somewhere random, and it comes from the cancellation between those diagrams. Yeah. Yeah, I probably overemphasized it here. Okay, other questions before I tell you a few things that are wrong with this? Okay, so this is pretty cool, actually, because it used to be we thought we couldn't measure the Higgs width at all, and now we've got a limit with assumptions that it's 4 to 5, times the standard model piece.
How much better did it?
I don't know, actually. Part of the problem is that those diagrams up there, the gluon initiated state first appears at one loop. So to do a little better theoretically, you need those guys to next to leading order, right? Which has just appeared. So that's two loop diagrams up there, and everybody knows that two loop diagrams are hard. So Kirill Melnikov has actually just calculated those, but I don't know how much better they project to do. The cross section goes up by a factor of 4 or something, going from 8 to 13 TeV. So that would say that maybe you go up by a factor of 2, because it goes by like square root of 2. So I don't know is the answer, but it's getting there, right? Okay, yes?
How does this compare?
Oh, that doesn't work at all, right? Because how would you do that? I mean, all we know now are branching ratios. We don't know the total width.
That seems to be standard cross
But you don't know the width to BB at the moment. BB, we don't have a measurement of. Gamma H goes to BB. And that's the dominant thing. It doesn't matter for branching ratios because analyses, but the biggest one is gamma H goes to BB, which we don't know, and we don't think we're going to know for a while. Okay? Anybody want to tell me why we don't know gamma H to BB? It's the biggest branching ratio. There's too much QCD crap is the answer, right? Yeah. There are proposals to look in odd regions of phase space to get it, but right now we don't know it. Yeah. Yeah. Mm-hmm. This is justifying this. So when you do the analysis, you use your favorite Monte Carlo and let gamma H run to fit to it. Yes. You don't use this. You say, aha, I know it's going to go like that. That I'm going to get information on the width by going above and on the resonance. Yeah. So it makes sense. So what would happen here? We know that on the resonance, everything looks pretty much standard model-like, right? So if the width is big, you would expect more events above the peak than you predict. So you run your Monte Carlo and you predict a number of events above the peak. And if you get more, you've got a big width. So you work through it that way. Okay. But yes, you do it right. Yeah.
So I understand that near the resonance area, most of the contribution is coming from exchanges because by definition the resonance.
Yeah.
And on the very high invariant mass state, again, it's going to be dominated by the exchange because it requires to have
The longitudinals.
Right. On the other hand, then should we expect to have some big chunk of contribution in the very low invariant mass region, which comes from the box diagrams, all that?
Well, they contribute all over the place, right?
Otherwise, yeah, I think it's going to be that the ratio can dramatically change of mass. Higgs really dominates in both areas properly.
Yes, yes. So that's why you know that here it looks like it's a standard model because that's what our measurements say.
Yeah.
So you count this is actually a counting experiment. So you count the number of events up here. You put some cut on. And you count the number of events, and then you compare it with your Monte Carlo, which includes the width in your Monte Carlo. And then you keep going by changing the width to see what your limit is. Right? Yeah. So you don't use this. This is just to justify why it
Oh, I
works.
see what you're saying.
Yeah.
You're saying the gamma parameter in Monte Carlo,
Yeah,
running and getting this.
Yeah, to get the number of events here, right? And then you get a limit. So if you had up here, 100 times the number of events you expected, that would correspond to a very big width. And that's how you get a limit. Yeah. Okay, so why is this kind of a swindle? Okay, it's kind of a swindle because we made these big assumptions. So for example, let's see here. Do I have any clean boards left? Yes. I've kind of assumed here what I want to prove, right? I mean, I've kind of assumed it's a standard model. suppose I have some effective Lagrangian term, which goes like some coupling over lambda squared times h over v times, say, b mu nu. Something like this. This is SU2 cross U1 gauge invariant term. So this is going to give me an HZZ coupling, which is actually going to grow with MZZ. Let's see, squared over lambda squared. Yeah. Okay. So couplings like this grow with energy. So if I had these EFT couplings, what's going to happen there? Well, actually, I do have a plot here which shows the standard model. Yeah. And it really looks just like that. Amazing. So what's going to happen if I have EFT couplings? So d sigma dm for lepton over m for lepton. Got my nice bump at the Higgs mass at mh. And then the standard model kind of goes flat. What's going to happen is it's going to go like that. Okay? So this isn't going to work at all if I've got these EFT couplings. Okay? Because these EFT couplings are going to give an increase in tail events, which is just what I was looking to measure in the first place for gamma h. So this whole thing assumes the standard model. Well, maybe it's because there's a big Higgs width. How would I tell the difference? Well, sure, it's interesting. That's why this is really a cool idea. And it's actually a really cool idea because it's got this physics of the longitudinal guys here. Yes. Okay? To measure this up here? Yeah. What you would get would be limits on this kind of coefficient, right? Yeah. Okay, so in my last few minutes, I think I'm going to continue with gluons and Higgs, okay? So, any more questions on this before yeah, go for it. Oh, count dimensions. These operators, this is dimension 4, so it's like 1 over lambda squared. So to get the dimensions right, you always get S over lambda squared when you use these EFTs. I mean, this is a general factor. I mean, generally in the EFTs, you have a 1 over lambda squared piece here. Okay? Actually, yeah, 1 over lambda squared. So to compensate for the 1 over lambda squared, there's an energy squared upstairs, which in this particular case is going to be the invariant mass of the Z pairs. Yeah. Well, let me see. I actually have a plot here of this guy. All right, O2, ... It goes, this particular operator goes like that, above the standard model, according to Jamie Gaynor. You take it up with Jamie. Oh, this guy? Yeah, why would it be? I mean, when you do this stuff, you have to calculate the whole thing. So actually, Jamie and his collaborators calculated all the operators that contribute to ZZ. And they all kind of, they look funny. They look above the standard model. And, like I said, yes?
Why is it lambda squared?
Yeah? Well, all right. This is, I want phi dagger phi here. Okay? Okay, so in my last few minutes, double Higgs production. Double Higgs production is awesome. And what I learned from you guys is that next time I do this, when I do these wiggles, I'll put in the factors of mz and 17 pi. Probably 12 pi's, whatever. The factors aren't hard to put in. And that'll make everybody happier, right? If I get all the factors, as opposed to the ones I think are important. Okay, so why do I want to measure double Higgs production? Okay, because I started with V is mu squared phi dagger phi plus lambda phi dagger phi squared, same normalization as Chaba, which is a miracle, equals mh squared over 2h squared plus mh squared over 2vh cubed plus mh squared over 8v squared h to the fourth. So we would like to know if the Higgs actually comes from the scalar potential, right? Okay, the scalar potential has two parameters, as we said, which we take to be V and mh. We know this guy. But in order to say that we've actually got the Higgs mechanism, we really want to know these guys, right? You really want to know what those guys are. This one? Is that good? Okay. Yeah, because this is going to be the cool part, so you'll want this. So you really want to measure this guy. But this guy involves the coupling of three Higgses. So how are you going to measure that? You're going to measure it. Glue goes to, here's the top, goes to H, goes to two H's. So here we go. All right, we're going to get that coupling, if it's a standard model one, whatever. And then there's also the stuff which is not too interesting. This is the top quark too. Goes to HH. Okay, so now for single Higgs production, I told you that the B quark contribution here was about minus 5%. For double Higgs production, it's like 2%. It's completely negligible. So the bottom quark doesn't come in at all. So if I want to actually see that this is the Higgs potential, I got to measure double Higgs production. Okay? So a couple interesting things. Actually, let me tell you the numbers before I tell you what's interesting. So sigma 13 TeV, it's 34 femtobarns. Okay? So it's got it, and that's before you put in branching ratios for the Higgs decaying to something you can see. So it's an extremely small rate. Okay? And it's not as sensitive to this coupling as you might have hoped, unfortunately, because what happens here is that 34 femtobarns? That's for 13 TeV. So at 13 TeV, glue goes to two standard model Higgses is 34 femtobarns. Okay. Including a factor of 2 for the higher order corrections. Okay. So if I go to my MT goes to infinity limit, which, like I said, I don't have to. I know how to calculate these things. But let's just go to MT goes to infinity for now. The amplitude is equal to some stuff, okay? And then it goes like 1 minus lambda 3 V over S minus MH squared times some more stuff. Where lambda 3 is just this guy. I'll call it lambda 3. Okay. So lambda 3 standard model is 3mh squared over V. Okay, there you go. So I want to measure the deviation from the standard model lambda 3. So this is the MT goes to infinity limit. So the first thing you notice, okay, so this guy here is a triangle, right? This is a triangle, and this is the box in some normalization, is that there's a minus sign between the two. So there tends to be a cancellation between the two. The other thing you notice here is that at threshold for making two Higgses, S is equal to 4mh squared. That's my threshold. So what happens at threshold? 0. The guy vanishes. Okay. So this thing is just really hard to measure. Okay. So this is great for you guys because many of you are model builders, right? So this is great. So it's a really small cross section. We're not seeing the standard model, but here's a resonance. Let's put in some new physics here. What should I call it? R. Build yourself a model, your favorite model, but just make sure it's got a resonance that's around twice the Higgs mass. Okay? So the standard model piece there kind of cancels at threshold, and you see this resonance piece. And so some of the model builders, say the MSSM people, the NMSM people, you can get enhancements here of a factor of up to about 40. So that's pretty cool, right? Okay, that would be good. Might actually see it. Okay, so let me stop and take questions. Okay,
So the
yeah.
dB bar width is known,
Is it?
measured by Atlas and
Okay, yeah. But you add them up, and you get nothing.
It's still invisible with, though.
Yeah, because you get nothing.
Still not full measurement.
Doesn't matter. And I'm betting the errors on that are humongous. Yeah, right.
I mean, this is 500%.
Yeah, so who cares? Also, there could be invisible width, which this method doesn't suffer from. Yes?
So if you have as close to MH, so not a repeat as a resonance,
Mm-hmm.
the doubling production,
Yeah?
it's like number 3 Starlink like diagram.
Mm-hmm.
Can you be more
Well, you're actually sensitive. The numbers, which I looked up, are that with 3,000 inverse femtobarns, you will be sensitive that lambda 3 is either less than minus 1.3 or greater than 8.7. And that's just because the rate is so small. So for people who are fans of 100 TeV collider, this process is the number one argument for the 100 TeV collider. Yeah. That you might be able to measure it there because the rate goes up by a factor of 40 actually for the 100 TeV collider. Okay? Yeah? Jeff?
Is there an intuition as to why the cancellation happens when you're on threshold?
Why does... Well, yeah. I mean, cross-sections always vanish at threshold, right? This particular piece, the reason is that you're making... that's actually an important point. You're making a 2-to-2 process. So you not only have the spin 0 piece, okay, so this is a spin 0 piece. We'll call it P0. But there's also a spin 2 piece, okay? And the spin 2 piece goes, well, the spin 2 piece vanishes and the MT goes to infinity limit. It goes like PT squared over MT squared. Okay, so the point is that it's all in the spin 0 piece. So you don't have anything here from the spin 2 piece. And the spin 2 piece is entirely from the box diagram. This one here? Well, you can't make 2 Higgses below threshold, right? So there is no below threshold. If I wrote the whole amplitude, the amplitude would be some function of the invariance times the spin 0 propagator plus some other function of the invariance times the spin 2 propagator, right? Or the spin 2 projector. All right, that's the full amplitude. And this guy vanishes in the high energy limit. And you only get this guy, which is sensitive to lambda 3. Yeah. Did that answer your question?
That's why it's not possible, they're not considered functional.
Oh, no. This is just on threshold. Yeah. Yeah.
How does the rate change if you add
Oh,
as like for the new physics?
yeah. Well, the thing about this, which is actually very amusing for all you model builders, right? You can't mess up the rate for glue goes to standard model Higgs, right? So whatever you do, you can't mess that up. Okay? So because it's the same diagram here. So remember I showed the example yesterday that vector-like quarks don't mess up glue goes to Higgs. So the model builders for the 750 GeV guy tend to put in symmetries so that they can't talk to the standard model Higgs. Yeah.
So from the low energy theorem, even this diagram also will have the same property. The second,
This one? This one.
right, will also have the same property that it was vector like.
No, it's different. No.
Oh, it is.
It is, right. Because the vector-like quark here relies on the fact that this is cosine squared plus sine squared, whereas this guy, will be cosine to the fourth or whatever. So it does come in on those guys. Yeah. Yes?
What is the intermediate state in the MSSM?
Oh, probably, well, not probably. It is the heavier neutral Higgs. Yeah. People have actually, it's the heavier neutral Higgs. And what you have to do is you have to kind of stand on your head and arrange all the other parameters so it comes out just right. So the NMSSM is actually easier because you got more parameters to play with. Yeah. Absolutely. And the singlet, since I've written papers on that, is even better because it's not constrained like the MSSM. You could just make stuff up, right? It's way better. It's easier. Yeah, the singlet could do it too. Any resonance will do it, as long as you make sure it doesn't mess up standard model Higgs production. Yeah. Okay. Yes?
Low energy theorem, but you're running kept that.
Yeah, I like the low energy theorem.
Yeah, so that's the better. Here, we are saying every conduction channel or
Anything.
so then should I be no matter what.
Assuming, well, what does this assume? This assumes that it couples proportional to the mass, right? There's that M over V up there. So if, for example, I'm in the MSSM 2 Higgs doublet model or something, you put like a GF up there, a coupling, so it would be like G times the mass. And then it all follows through, too. But the assumption is that it couples proportional to its mass times some coupling. Right. So, for example, if all the coupling were Dirac, it wouldn't work. But it does work for, say, vector fermions, because it picks out that piece. Yeah. Right. And in fact, there's a long literature on the subject putting in those couplings just right. Yeah. Okay. Yeah. It's really M. And this thing turns into the determinant of M if you've got a matrix of M. Yeah. So no, you can't think of it as scale in new physics. You think of it's got to be a particle which couples proportional to its mass with some coupling. Yes. Yes. Mm-hmm. Yeah. Okay, you had one more question. Yeah. Yeah, absolutely. Mm-hmm. People do that, yeah. And the argument goes the same. Yeah. Okay. Yeah. Okay, that's it. Yeah. Now you can ask me more questions. What do you want to know?
But for the vector bosons, then we have a mass lighter than the Higgs, and you took the pH equal to 0 limit.
Yeah,
so,
so
isn't it pretty tricky?
yeah, well, you got to have heavy vector bosons.
Oh, I see.
A
So
new
it's
model.
like not the standard model. Vector
Yeah,
vectors.
people did this when they thought that the Higgs was 45 GeV.
I see.
Yeah,
Okay.
yeah, right.
All right,
But,
thanks.
yeah.
So I have a quick question. So you see this tail behavior.
Yeah.
So what do we expect afterward? Like in the symptotic, we have expect a sharp drop, like in the central mass. Like
Well, eventually it's going to fall off because there's no energy, right?
yes, but what do we expect? Just like
It probably falls. Actually, I brought a plot here. Okay, so
yeah, I wondered.
this guy is the standard model. So way out here, see, look at the scale. It goes out to 10
Oh,
TeV.
I
So,
see. So it's
you know, it's
actually-
pretty flat
yeah,
for a
yeah.
while before it falls off. Yeah,
I see.
yeah.
So it's harder to predict what's going on.
There are no events out there. I mean, it invariant
Of course,
massive
of
of
course.
TeV.
Yeah, yeah, I
I mean,
understand.
they took it to 10 TeV.
Sure,
Just-
sure.
I didn't know about that width analysis.
Is that cool or what? I mean, it's like
The width of the Higgs is like 4 MeV.
4 MeV. It's like, why didn't I think of this? Because it's just physics.
Because the width is so small that it's sensitive to it.
Yeah, it really is.